Imagine dropping your phone and watching it fall to the ground. That simple, everyday moment is actually one of the universe's most profound mysteries in action. The force pulling your phone downward has shaped everything from the tiniest pebble to the largest galaxy, and without it, you literally wouldn't exist. Gravity is the invisible sculptor of our cosmos. It's the fundamental force that causes any two objects with mass to attract each other, whether they're bowling balls or black holes. But here's where it gets mind-bending. According to Einstein's general relativity, gravity isn't really a force at all. It's actually the curvature of space-time itself, warped by the presence of mass and energy. Think of it like placing a bowling ball on a trampoline. The fabric bends and marbles rolled nearby will curve toward the ball. That's essentially what massive objects do to the fabric of space and time. The importance of understanding gravity extends far beyond academic curiosity. Every time you use GPS on your phone, you're benefiting from our precise knowledge of gravitational effects. In fact, if we didn't account for gravitational time dilation, the phenomenon where time runs slower in stronger gravitational fields, the entire GPS satellite system would fail within just 2 minutes. That's right, your feet are actually aging slightly slower than your head right now because they're closer to Earth's gravitational center. This force has enabled humanity to launch satellites, navigate spacecraft to distant planets, and predict the movements of celestial bodies with extraordinary precision. It governs ocean tides, shapes weather patterns, and keeps our feet firmly planted on Earth's surface. Without gravity, stars couldn't form, planets couldn't orbit, and galaxies would simply drift apart into cosmic loneliness. Perhaps most remarkably, scientists recently detected gravitational waves, actual ripples in space-time caused by colliding black holes billions of light years away. These discoveries continue to revolutionize our understanding of the universe, helping us probe mysteries like dark matter and dark energy. From the gentle arc of a basketball to the violent collision of neutron stars, gravity touches everything. It's a force so familiar we rarely think about it, yet so strange that it challenges our deepest understanding of reality. As we explore this fundamental force together, prepare to see the world around you in an entirely new light, or should we say, an entirely new weight. The story of gravity begins thousands of years ago with a simple observation: things fall down. Ancient Greek philosopher Aristotle thought he had it figured out around 350 BCE. Heavy objects, he declared, fall faster than light ones because they're more eager to reach their natural place at the center of the universe. This made perfect sense to everyone for nearly 2,000 years. After all, doesn't a rock seem to fall faster than a feather? But in 1589, a rebellious Italian professor named Galileo Galilei decided to actually test this ancient wisdom. Legend says he dropped cannonballs of different weights from the Leaning Tower of Pisa, though he probably never performed this exact experiment. What Galileo did discover through careful measurements was revolutionary. In the absence of air resistance, all objects fall at exactly the same rate. By 1604, he'd worked out the mathematics, showing that falling objects accelerate uniformly and the distance fallen increases with the square of time. This discovery shattered 2 millennia of accepted truth, but the real revolution came from a young man sitting in his mother's garden during the plague years of 1665. Isaac Newton, just 23 years old, watched an apple fall and had an extraordinary thought. What if the force pulling that apple down was the same force keeping the moon in orbit around Earth? This annus mirabilis, or miracle year, saw Newton develop the foundations of calculus, optics, and universal gravitation. When Newton published his Principia Mathematica in 1687, he gave the world a precise mathematical formula showing that every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. Suddenly, the movements of planets, moons, and comets could be calculated with stunning accuracy. The triumph of this theory came in 1846, when mathematicians used Newton's equations to predict the existence and location of Neptune based solely on wobbles in Uranus's orbit. But Newton's gravity had a troubling mystery. How did massive objects instantly know about each other across vast distances? This puzzle haunted physicists for over 2 centuries until a patent clerk in Switzerland proposed something radical. In 1915, Albert Einstein published his general theory of relativity, completely reimagining gravity not as a force, but as the curvature of space and time itself. Mass and energy, Einstein showed, actually bend the fabric of space-time, and objects follow the straightest possible paths through this curved landscape. The world was skeptical until 1919, when British astronomer Arthur Eddington led an expedition to observe a solar eclipse. His measurements confirmed Einstein's prediction that massive objects like the Sun bend light itself. Overnight, Einstein became a global celebrity, and our understanding of gravity was forever transformed. This journey from Aristotle to Einstein spans over 2 millennia, each discovery building upon previous insights while overturning long-held beliefs. Today, scientists continue pushing the boundaries, detecting gravitational waves and imaging black holes, proving that the story of gravity is far from over. Every single object in the universe is pulling on you right now. That coffee cup on your desk, the moon overhead, even distant galaxies billions of light years away, they're all tugging at you with an invisible force. This is the first fundamental principle of gravity: universal attraction. Every object with mass attracts every other object with mass, no exceptions. It's like having magnets that only attract and never repel, except this force works through empty space and affects everything made of matter. The strength of this attraction follows a beautifully simple rule called the inverse square law. Double the distance between two objects and the gravitational force becomes 4 times weaker. Triple the distance and it drops to 1/9. Picture a flashlight beam spreading out in the darkness. At twice the distance, that same amount of light has to cover 4 times the area, making it dimmer. Gravity weakens in exactly the same way. This explains why you don't feel the pull of that coffee cup, but you definitely feel Earth's gravity. The cup is close, but has tiny mass, while Earth is massive enough to overcome the distance between you and its center. Here's where things get weird. Albert Einstein realized something extraordinary. Being in a gravitational field feels exactly the same as being accelerated. This equivalence principle means you literally cannot tell the difference between standing on Earth and being in a rocket ship accelerating upward at 9.8 meters per second squared. Remember that feeling when an elevator starts moving up and you feel momentarily heavier? That sensation is indistinguishable from experiencing stronger gravity. Your body can't tell the difference because, fundamentally, there is no difference. This insight led Einstein to an even more mind-bending realization. Gravity isn't really a force at all. It's the curvature of space-time itself. Mass and energy actually bend the fabric of space and time around them. Imagine a bowling ball sitting on a stretched rubber sheet. It creates a dip, and if you roll marbles nearby, they'll curve toward the bowling ball. They're not being pulled by a force, they're simply following the straightest possible path through curved space. That's exactly what planets do when they orbit the Sun. They're traveling straight through space that's been curved by the Sun's enormous mass. This warping of space-time creates another bizarre effect: gravitational time dilation. Time literally passes more slowly in stronger gravitational fields. If you lived your entire life at sea level while your twin lived on a mountaintop, you'd age slightly slower than them. The difference is incredibly tiny. We're talking nanoseconds over a lifetime, but it's real and measurable. GPS satellites have to account for this effect, or they'd give you the wrong location within days. It's as if gravity creates zones where time itself flows at different rates, like rivers moving at different speeds. The variation in gravitational pull across an object creates tidal forces. The side of Earth facing the moon experiences stronger lunar gravity than the far side, stretching our planet slightly and creating ocean tides. For objects venturing too close to massive bodies, these tidal forces can be catastrophic. Near a black hole, the difference in pull between your feet and head could literally stretch you like taffy. Astronomers cheerfully call this spaghettification. Understanding these core concepts reveals gravity's true nature. It's not just about things falling down. It's about the very structure of space and time, the paths planets take through the cosmos, and even the flow of time itself. From the gentle arc of a thrown baseball to the spiral arms of galaxies, from the formation of stars to the ticking of clocks at different altitudes, gravity shapes every aspect of our universe. What seemed like a simple force pulling things together turns out to be the universe's way of telling mass and energy how to move through the fabric of reality. And that fabric, in turn, is shaped by the very objects moving through it. It's an elegant cosmic dance where space, time, matter, and energy are all interconnected, following rules that we're only beginning to fully understand. So how do we actually know gravity works the way it does? Scientists don't just make theories and call it a day. They test them relentlessly. The evidence for our understanding of gravity comes from centuries of clever experiments, each one building on the last. It all started with Galileo in 1589. Legend says he climbed the Leaning Tower of Pisa with two spheres, one heavy, one light, and dropped them simultaneously. To everyone's shock, they hit the ground at nearly the same time. This simple experiment shattered Aristotle's 2,000-year-old idea that heavier objects fall faster. Galileo had just proven that gravitational acceleration is the same for all objects, regardless of their mass. But knowing how things fall doesn't tell you why they fall. Fast forward to 1798, when Henry Cavendish performed one of the most delicate experiments in physics history. In a shed on Clapham Common in London, he built an incredibly sensitive device called a torsion balance. Using lead spheres, he measured the tiny gravitational attraction between masses in his laboratory. This wasn't about Earth's pull. This was about the attraction between ordinary objects. His experiment gave us the first accurate measurement of the gravitational constant, that crucial number that appears in Newton's equations. Suddenly, we could calculate the mass of Earth itself. The precision kept improving. Between 1885 and 1909, Hungarian physicist Laurent Eötvös pushed the limits even further. He wanted to know if different materials fall at exactly the same rate, or just mostly the same rate. Using an even more sensitive torsion balance, he tested whether wood, platinum, copper, and other materials responded identically to gravity. His answer? They're identical to 1 part in 100 million. This wasn't just impressive accuracy, it was a hint that gravity might be something more fundamental than just a force. Einstein took that hint and revolutionized our understanding. But revolutionary ideas need revolutionary proof. In 1919, Arthur Eddington led an expedition to Principe Island off the west coast of Africa to observe a total solar eclipse. Einstein had predicted that massive objects like the sun would bend the path of light. During the eclipse, with the sun's glare blocked, Eddington photographed stars near the sun's edge. When he compared their positions to photographs taken months earlier, the stars had shifted exactly where Einstein predicted. Light was bending around the sun. Gravity wasn't just pulling on matter. It was warping space itself. The evidence kept mounting. In 1959, Robert Pound and Glenn Rebka Jr. carried out an experiment in a tower at Harvard University. They shot gamma rays up and down the 22.5-meter tower and measured tiny changes in their frequency. The result? Time runs slightly faster at the top of the tower than at the bottom, exactly as Einstein predicted. Gravity doesn't just affect space, it affects time too. The most spectacular confirmation came in 2015. The LIGO detectors, massive installations in Washington and Louisiana, with laser beams running through 4-kilometer-long arms, detected ripples in space-time itself. Two black holes, 1.3 billion light-years away, had spiraled into each other and merged, sending gravitational waves across the universe. These waves stretched and squeezed space as they passed through Earth, changing the length of LIGO's arms by less than 1,000th of the width of a proton. Yet that tiny change was enough to detect. From dropping balls off towers to detecting cosmic collisions, each experiment has confirmed and refined our understanding. Today, your GPS navigation works only because it accounts for gravitational time dilation. The evidence isn't just in textbooks, it's in the technology you use every day. Every time you take a step, flush a toilet, or check the time on your phone, you're experiencing gravity in action. We tend to think of gravity as just the thing that keeps us stuck to Earth, but it's actually the invisible architect of nearly everything in our daily lives. Consider your morning routine. When you stumble out of bed, gravity immediately takes charge. It pulls you toward Earth's center, creating the sensation of down that your inner ear uses to keep you balanced. Without this constant pull, you couldn't walk, run, or even stand upright. You'd simply float away like an untethered astronaut. That refreshing morning shower? Thank gravity for that too. Water towers and elevated tanks use gravitational pull to create pressure in your pipes. Water naturally flows downward, delivering itself to your home without constant pumping. This simple system saves enormous amounts of energy and keeps water flowing even during power outages. The same principle makes your toilet work. Gravity pulls water and waste through the pipes, creating that satisfying flush without complex machinery. But gravity's influence extends far beyond basic plumbing. Your smartphone contains tiny accelerometers that measure gravitational acceleration, determining which way is down so your screen can rotate automatically. Every time you count steps or play a motion-controlled game, you're using technology that depends on detecting gravity's pull. Speaking of technology, GPS satellites orbiting over here. Where does gravity research go from here? We're living in a golden age of gravitational discovery. In 2015, LIGO detected gravitational waves from colliding black holes, 1.3 billion light-years away, ripples in space-time itself that Einstein predicted a century ago. Then in 2019, we got our first actual photograph of a black hole's event horizon, confirming what the math had told us about extreme gravity. But here's the thing. Gravity is still the rebel of physics. While we've unified the other three fundamental forces with quantum mechanics, gravity refuses to play nice. This isn't just an academic problem. Without a quantum theory of gravity, we can't understand what happens inside black holes or in the first moments after the Big Bang. The mysteries pile up. Dark matter and dark energy make up 95% of the universe, yet our gravitational theories can't explain them. Some scientists think dark matter is invisible particles. Others propose modifying gravity itself. The debate rages on. Right now, thousands of researchers are attacking these puzzles from every angle. String theorists at Princeton envision vibrating strings in 11 dimensions. Teams at Perimeter Institute explore loop quantum gravity, where space itself is made of tiny loops. The Event Horizon Telescope continues peering into black holes, while LIGO and its partners detect cosmic collisions weekly. The next decade promises even more. The LISA Space Telescope will detect gravitational waves from supermassive black holes. New experiments might finally reveal whether gravity behaves differently at microscopic scales. From Galileo dropping balls to detecting cosmic ripples, we've come impossibly far. Yet gravity keeps its deepest secrets. Perhaps that's what makes it so captivating. This force we experience every second still harbors profound mysteries about the nature of reality itself.